What if the best person to solve the mystery of alien communication isn't a SETI researcher, a radio astronomer, or even an actor or an actress, but instead is a theoretical physicist trained in the deepest notions of physical law, symmetries, and quantum field theory? Well, today I'm speaking with an expert, Latham Boyle, whose day job is to explore the fundamental symmetries of the universe and perhaps develop new ideas to understand how the universe began and how it would relate to the groundbreaking data that new experiments like the Simons Observatory and others are coming up with. But he has even more to his research repertoire than just that. Perhaps the answer to one of the greatest paradoxes of all time, the Fermi Paradox. The universe teems with life. Where are the aliens? I think you're going to love the deep dive that we go into and solving perhaps the physics of communicating with aliens and solving the Fermi Paradox once and for all. So Latham, thank you so much for joining us today from Edinburgh.
Oh, well, thanks so much for having me. It's a pleasure to speak with you.
Like I said, I've wanted to have you on for quite some time. We had your colleague, Neil Turok, on for his second appearance just recently. I do want to get to that topic of the Fermi Paradox and your unique kind of solution to it, which resonates with a completely different part of my brain than any of the resolutions that I've heard before. But as I said, before we get to that later on in the interview, I really want to understand what drives you working on these deep mathematical mysteries and uncovering and maybe predicting new structures that ties all your research together. It seems like you have a thread that goes through it, and it's asking these big questions. So how did you get here? How did you get to this kind of unique position where you could be as conversant talking about mirror universes as the Fermi Paradox?
I don't really think of myself as an expert on the Fermi Paradox. There's a lot of people who are much more expert on it. I just realized one thing that hadn't been pointed out about it that seemed important to me. I guess I've worked on the things that struck me as the most fascinating. And I find that if I work on what I'm most interested in, that I'm much more productive. And if I try to work on what someone else is interested in, I'm incredibly unproductive. I just end up wandering around to whatever. I think that's the best I can tell you. I don't know exactly why the particular topics I'm interested in have grabbed me.
Let's talk about this, the mirror universe. And first of all, let's define some terms for the audience that might not be as familiar with your research. What are symmetries? And in particular, what is the importance of CPT symmetry and its violations?
Well, symmetry in general refers to any change that you can do to anything that leaves it the same. So the most famous example is mirror symmetry, where if you reflect something in a mirror and it looks the same. Another example would be if you have a cube, all the different ways you can rotate the cube that, if you rotate it by 90 degrees about any axis, connecting two opposite faces, that'll carry the cube into itself. But the laws of physics have a lot of symmetries. That seems to be the most basic principle we know that's emerged over centuries of research as kind of the organizing principle for how the laws, as we best understand them, can be described. They are the laws that have such and such symmetries in which the constituent fields and particles transform in such and such a way under those symmetries. In particular, CPT symmetry is believed to be an exact symmetry of the laws of nature, and it's the symmetry where you reflect a process in a mirror and then run it backward in time, and then also replace every particle by its antiparticle. And if you do any of those three things by itself, it's not a symmetry of the laws of nature. But if you do all three of them together, it is. And that's believed to be a symmetry of the law of nature. It's believed to relate any microscopic process to another related microscopic process that has the same amplitude, people say. The amplitude is the quantum mechanical quantity that you calculate from quantum mechanics, and then you square it to get the probability of that process happening. But the universe as a whole, if you just look at the portion of the universe after the Big Bang, doesn't naively seem to have that symmetry. It seems that there's a particular going one direction in time away from the Big Bang, where the universe expands and cools, is very different than the other direction in time, where it gets hotter and you go back toward the Big Bang. So that was one of the things that led us to this alternative picture that we've been getting more and more excited about over the past few years, is developing a picture of the cosmos in which it actually does respect CPT symmetry, and then trying to understand what a model like that can explain about the observed cosmos and what it can predict for future experiments.
With Neil, was there sort of an exact moment when you both realized the math was pointing you to somewhere some would say pretty radical.
I don't think there was. I think there have been a lot of steps along the way. Theory really didn't fall into place all at once, and really it still hasn't completely fallen into place. There's still a lot of stuff we don't understand. But I guess maybe the starting point was that I think we had both come to the view that the dominant theory of the early universe, the inflationary picture, I guess we both have had the gut feeling that it probably was not correct. According to that picture, if you look back toward the Big Bang, well, when we look back toward the Big Bang, we see that as we look further back, as we look back close to the Bang, as far back as we can look, we see that the universe becomes dominated by radiation, by a plasma of hot particles and photons. But according to the inflationary picture, if you looked even further back, that radiation-dominated era would end, and there would be an earlier period, the inflationary period. But because we began to suspect the inflationary period didn't exist, we began to think about, well, what if the radiation-dominated period just extended all the way back to the Big Bang? And when you do that, that solution to Einstein's equations for gravity just naturally extends through the Big Bang and is symmetric around the Big Bang. And so it has this property. It can be extended through the Big Bang. And then once you do that, you find it can be symmetrically flipped, reflected through the Big Bang so that the portion after the Big Bang gets swapped with the portion before the Big Bang. One's first inclination is to say, oh, maybe that's just a mathematical artifact and to not really pay attention to it. But, historically, it's usually not a good idea to do that. Time and again, if the laws of physics tell you something, the best laws you know at the time seem to have a solution with such and such a striking property. It's usually a good idea to at least take it seriously and see where, or at least see where taking it seriously leads. And so I think that was kind of the start, is that we began to think about, oh, what if we did take that seriously? What if it's not just an artifact? What if it's a real hint? And then, that led to us to realize, wait a minute, actually, if you do that, if you just, then to be consistent, there should be a reflecting boundary condition at the Big Bang, which is like, if you look at an ordinary mirror, the reason you see an image of yourself on the other side of the mirror is that the electromagnetic fields, the silver atoms on the mirror, conduct electricity, and they force the electromagnetic fields at the mirror, at the surface of the mirror, to satisfy a special property called a reflecting boundary condition. And it makes it look like there's another copy of you on the other side of the mirror. We realized if the universe really is symmetric about the Bang, as the solution I just mentioned seems to suggest, then the fields there should satisfy a reflecting boundary condition. But then we were just struck, wait a minute, actually, a reflecting boundary condition is exactly what the observed primordial perturbations do satisfy. You have worked on cosmic microwave background experiments. You've done these great experiments that measure in detail the properties of the primordial perturbations by measuring this snapshot that the universe took of itself 370,000 years after the Big Bang. That's cosmic microwave background. The most famous thing about that snapshot is that if you plot power spectrum, you see this beautiful ringing curve with peaks and troughs. And if you just ask, why is that? Why is there that ringing spectrum? Why does it make that kind of sinusoidal pattern? And why are the peaks and troughs precisely where they are? Well, there's a usual way that's described in inflation. In inflation, it's described by saying that there was a period of inflation and cosmological perturbations got dragged outside the horizon and froze. That's what set their initial conditions. And then because they all froze together, then once they started oscillating, they all oscillated in sync with one another. And that's what created the ringing pattern in the CMB. Another way to say it is just that if there was no inflationary period and you just follow the radiation-dominated epoch all the way back to the Bang, the exact same thing amounts to the statement that those perturbations satisfy a reflecting boundary condition at the Big Bang. That's what synchronized them in exactly the way that we see. Those two starting observations were the thing that really got us excited, really thinking like, wait a minute, there might be a simpler explanation for what's going on and we should think more about it.
And yeah, when I talked to Neil about this, I said, you guys in Edinburgh right now should be more conversant than almost anyone in the universe about the importance of symmetry breaking, because of course Peter Higgs, the late great Peter Higgs. So isn't it true though that most of the interesting facts about our universe owe their existence to symmetry violations. I mean, if there were equal amounts of matter and antimatter, this would be a tough conversation to have. So how do you reconcile that, kind of the existence of theoretical physicists with a perfect symmetry? Or is there perhaps a hint that maybe even sacrosanct, principles like CPT might get violated at a critical condition, say, near the origin of our universe?
Well, on the one hand, if you can really summarize the progress in theoretical physics over the past few hundred years in one word, it really would be symmetry, that there are these fundamental governing symmetries that seem to essentially define what the laws of nature are. And in a sense, learning the laws of physics has essentially amounted to learning from the observations what the right symmetries are. What are the actual symmetries governing the fundamental laws in our universe? Then, there's the symmetries in the laws of nature, and then there is the actual state of the universe, which is not necessarily as symmetric. That's the first distinction I would draw, is that these symmetries, gauge symmetries that define the standard model, SU3 times SU2 times U1 is the gauge group of the standard model. That could very well be exact. I suspect that is an exact symmetry. Well, who knows? But anyway, that as far as we know, that's exact. And the basic symmetry of Einstein's theory of gravity is a symmetry called diffeomorphism invariance, basically the symmetry to choose different frames of reference. Different observers at different places in the space-time can all choose different frames of reference. And that could very well be exact also. Then the state of the universe itself can violate those symmetries. But there again, it's a very fascinating interplay, because if you look back in the early universe, the state of the early universe was vastly more symmetric than it is today. I mean, today it's this very inhomogeneous place where there's some places where it's very dense and a lot of interesting stuff is going on, like here on Earth. And then there's other places deep in a void where there's almost no matter. It's almost pure vacuum and nothing's going on. But then if you follow it back to early times, the state of the universe got very symmetric, very homogeneous and isotropic, almost perfectly so. But then there was, like you say, there were these tiny little deviations from that perfect homogeneity and isotropy, tiny little perturbations, which ultimately were responsible for everything interesting that happened. I mean, they grew into galaxies and planets and ultimately, led to, at least in our neck of the woods, things coming to life and everything interesting. So somehow the interplay of those two things, I think, is not very well understood, but it's what it's all about. I agree with you.
You mentioned life forms, and we have to get to the Fermi Paradox to answer the question if there are other life forms, and if so, why are they concealing themselves so effectively? We'll get to that. But I do want to go through you're gracious enough to prepare some slides for advanced layperson level, and I think it would be good to kind of go into those I like to avoid, too much overproduction, but to understand what a CPT symmetric mirror universe concept really would imply and why we might want to find such a universe or look for it, at least in the context of, as you mentioned, the experiments like our Simons Observatory. So why don't we share your screen now?
I'll try to introduce the basic idea and why we've begun to take it more and more seriously as a possible alternative explanation of the early universe. My subtitle here, what is the simplicity of the early universe trying to tell us? So let me give you the gist. So here's a cartoon picture of the expanding universe where time tau, the conformal time tau, runs up the slide. The cartoon shows a picture of the universe that's like an inverted lampshade or a cone with its tip cut off, with a kind of small circle at the bottom, the very small early universe, expanding as we go up the slide to a large circle at the top, the big universe we live in today. We're sort of standing at the top, we're living on that big circle at the top, and we look back with our telescopes toward the tip of the cone, but we can't see all the way back. The universe becomes opaque. If we try to look too far back, the universe becomes too dense and it becomes opaque. So we can't see all the way back to the bang, but we can see very close. We can see rather directly to a few 100,000 years after the bang, the cosmic microwave background that you and your colleagues have been measuring better, more and more beautifully over the years. And then more indirectly, based on, but still with quite good certainty, we infer, or see in quotes, back to a fraction of a second after the bang. And in either case, what we see is very striking for its simplicity. In summary, the simple fact that's been observed is that the closer back you look to the Big Bang, things get simpler and simpler in all ways that we've thought to check. So that includes, first of all, if you look at the background universe, it's almost perfectly symmetric, homogeneous, isotropic, and spatially flat. So homogeneous just means so if we took a snapshot of the universe a fraction of a second after the bang, if you moved from one point to another in the snapshot, the conditions are virtually identical from one point to another. Same temperature, same density. And isotropic means if you looked one direction in the snapshot and then turned and faced in a different direction, things again would look identical to you in either direction. And then also the geometry of the snapshot is flat, just like flat three-dimensional space. The four-dimensional universe is curved because of Einstein's equations, but the three-dimensional slice of the universe, well, it could have been curved, but it's observed to not be. Observationally, we know that it's almost perfectly flat. So much for the background, but then if you zoom in, it's like if you looked at the Earth from very far away, if you see a picture of the Earth taken by a satellite far away in the solar system, it looks like an almost perfectly round, smooth marble. But as you get closer to it, you see that there's tiny, you begin to see, there's actually peaks and troughs, mountains and valleys, bumps on the sphere. And it's like that in the early universe too. It's almost perfectly symmetrical. But if you look closely enough, there's tiny perturbations in the temperature and density as you move from one place to another. Those are of order 10 to the minus 5, an order a few parts in 100,000. So very, very tiny. But they too turn out to be as simple as possible. They're as simple as they can be, and again, in every way that people have thought to check. In particular, I've given 3 more properties here that they are found to satisfy. They're purely scalar perturbations, meaning it's purely perturbations in the temperature and density from place to place. There's no evidence for any vorticity or primordial gravitational waves in the early universe, which are the other 2 types of perturbations that could have been there.
Then we should say, there could be evidence.
So far, there's no evidence for anything but purely scalar density perturbations. That's a good point. Yeah, the same goes for all of these things. The second point is that so far they seem to be, their correlations, the statistical correlations between the perturbations at one point and another seem to be described by purely Gaussian, nearly scale invariant correlation functions. No evidence for any violation of Gaussianity or of a pure power law in the correlation functions. And then finally, as I mentioned, the third way in which they're special is that the phases are all perfectly in sync with one another. And indeed, they're synchronized exactly in such a way that as you follow them, if you think of any of the perturbations, as you follow the universe forward in time, they oscillate in time. But if you follow it backward in time, all of the perturbations in the universe, if you imagine splitting them, we call it Fourier decomposition. If you imagine splitting this field of random perturbations into each separate wavelength of perturbation and following each wavelength separately, each wavelength is oscillating in time, but if you follow it back, they're all simultaneously reaching their maximum of their oscillation right as you get back to the Big Bang. Physicists will recognize that as a reflecting boundary condition. It's called a Neumann boundary condition that they satisfy, and that's responsible for the oscillating pattern we observe in the CMB, like I mentioned before. That was one of our early motivations for taking seriously this picture that the Big Bang is a mirror. What is the usual story in early universe cosmology? So the hint is that the closer back you look to the Big Bang, the simpler things get. That's the sort of fundamental clue that we're given. And the goal, the central topic in early universe cosmology is to understand that hint. What is it trying to tell us? According to the conventional picture, the idea is the following. The conventional picture is, okay, it's true that things get simpler and simpler as you go backward in time, all the way back to a fraction of a second. As far back as we can see, things get simpler and simpler. But if, according to the standard story, if you could see even further back, you would discover that trend was an illusion. That if you could see back even further, you would see that even earlier there was a big mess, a very inhomogeneous, messy universe with maybe giant fluctuations in the curvature and temperature and density from place to place, a very chaotic beginning. And according to that view, the goal of a theory of the early universe is to explain how that messy initial state got transformed into the pristine, symmetric, simple state that we actually can see. And so the idea of inflation is basically that there was a period in between those two, in between the mess and the simplicity, that there was a period of very rapid exponential stretching of the universe. And effectively, that stretching has the result that when we look back, our past light cone, the portion of the universe that we can see using our telescopes, effectively gets zoomed in on such a tiny piece of the mess that we can't see how messy it is. We end up just seeing a tiny little speck of the initial messiness that has been stretched out so much that we can't see what a mess it was part of. It looks like the simple state we see. That's the usual story. But, Neil and I were interested in seeing if we could take the observations more at face value. As far back as we can see, it looks like the further back you look, the closer to the Big Bang you look, the simpler things get. Maybe the universe is just trying to tell us that that's what's going on. For some reason, as you follow things back to the Bang, things get extremely simple in the way that we observe. And, maybe what we should do is just try to take that observation at face value and see where it leads. As I mentioned, so if you do that, then, we know what the solution of Einstein's equations looks like in the very simple early phase that we can see. And if you just take it seriously, then it has this property that you can analytically extend it. It has a very particularly simple structure where the full metric of space-time, the shape of the space-time is very simple. It's just flat space, but times an overall scale factor or conformal factor that stretches the universe with time and does it in a particularly simple way. It's just proportional to the conformal time tau itself. And so unlike most singularities in general relativity, so if you follow this solution back, you eventually get to the tip of the cone, the place where the conformal factor, the scale factor, touches zero. So that's an example of a singularity. Most singularities in Einstein's theory of gravity are a mess. You can't analytically extend the space-time through them. But this one is very special in that regard because the singularity is purely a momentary vanishing of the conformal factor in front of the metric. And because the vanishing has this very special property, it's just a simple zero, just proportional to 1/power of the time. It's unambiguous how to extend this, and it's just you just let the time extend to negative values. You don't cut it off when tau equals zero. And if you do that, you find that the space-time extends to this double cone picture, like two ice cream cones touching at their point. And when you do that, you notice that the new extended space-time has a new symmetry under tau goes to minus tau, basically taking the two cones and swapping them with one another, or if you think of it as an hourglass, flipping over the hourglass. More correctly, the proper thing is the real symmetry involved here is the one that I mentioned before. It's a version of CPT symmetry that I described earlier. So let's try to take this seriously. As I say, the fact that there's this extension of the solution describing our universe in the past that has this reflection symmetry. Again, one perspective is that it's just a mathematical artifact and doesn't have anything to do with reality. Maybe that's the case, but let's try to take it seriously and see where it leads. And the interesting thing is that if you do take it seriously, it ends up giving new explanations for a bunch of things that we see about the universe that we hadn't previously thought of as being explained in this way. This is a figure that I've stolen from Stuckelberg's great 1930s paper where he invented the idea that an antiparticle is just a particle traveling back in time, which is very connected to this idea of CPT. You might think of there as being a sense in which these two halves of the universe are a bit like a universe-anti-universe pair forming out of the Big Bang, in analogy to how in Stuckelberg's picture a particle-antiparticle pair can nucleate at a given moment in time.
Is that only in a black hole or is that general?
That's general, yeah. Stuckelberg's picture where particles can nucleate. For example, this happens in a strong electromagnetic field. You can have this Schwinger pair production where a particle-antiparticle nucleates out of the vacuum like this. So I want to give a couple examples of facts about the universe that are explained if you take this reflection symmetry seriously, this sort of temporal reflection symmetry about the bang seriously. But to do that, it's helpful to use Roger Penrose's trick where instead of the two ice cream cone picture of space-time, we kind of blow up the singularity, expand the tip of the ice cream cone into a dashed circle in this picture so that it becomes like a straight cylinder. And so now the part of the cylinder above the sort of dashed circle equator is again the part of the universe after the Big Bang, and the part below the equator, below the belt, is the part before the Big Bang. And so now in this picture, this is called, these sort of diagrams, these Penrose diagrams are meant to show more clearly what the causal structure of the space-time is, in particular near the edges of the space-time, the boundaries, and near the singularities. And so what we see in this picture is that the Big Bang is a kind of spatial surface. At that surface, if we want to take the reflection symmetry seriously, there should be a reflecting boundary condition like at a mirror, but unlike a normal mirror where the direction perpendicular to the mirror is a spatial direction, this is a kind of exotic mirror where the direction perpendicular to the mirror is the time direction. But other than that, it's mathematically very similar. As I mentioned, a first thing that one finds, if one takes seriously that the fields should satisfy reflecting boundary conditions at this mirror, at the Big Bang, is that the scalar perturbations are synchronized in exactly the way we see in the cosmic microwave background. Okay, that it explains this famous ringing pattern that's observed and that's so where the theory and the data agree so beautifully. It also kills any vorticity. It turns out the reflecting boundary condition is incompatible with primordial vorticity or vector perturbations, which is good because they're not observed. And it's also incompatible with any singular perturbations, including the kind of primordial tensor perturbations or gravitational wave perturbations that would diverge, would blow up near the Big Bang and make it look very anisotropic in contrast to what we see. So it's also not compatible with an anisotropic Big Bang, which is, again, good because that matches what we see. We see a very isotropic Big Bang. What I wanted to tell you now is about how this same mirror idea provides a very elegant explanation, we think, for what the dark matter is. So the universe appears to be full of dark matter. Traditionally, people have considered particles beyond the standard model when they try to explain the dark matter. They talk about supersymmetric partners of the standard model particles, or they talk about axions. Many different particles have been considered. A crucial question is whether anything in the standard model can be the dark matter. Do we really need something beyond the standard model? Well, first we have to clarify what we mean by the standard model. So the original version of the standard model back in the 60s and 70s would have meant the particles in this figure that I'm displaying. In particular, there's 6 types of quarks: an up quark, charm quark, top quark, down quark, strange quark, bottom quark. And there's 3 types of charged leptons: electron, muon, and tau. And 3 types of uncharged leptons: the electron neutrino, the muon neutrino, and the tau neutrino. And then there's the force-carrying particles: the gluon, the photon, the weak bosons W and Z, and the Higgs particle. What I want to mention is that in this original version of the theory, all of the particles come in left-right pairs. There's every particle really comes in 2 variants: a left-handed variant and a right-handed variant, except for the neutrinos on the bottom line. In the original version of the standard model, the electron neutrino, the muon neutrino, and the tau neutrino were all thought to be just left-handed particles. But in the late 1990s, the Super Kamiokande experiment and the SNO experiment observed that neutrinos have mass and that they oscillate into one another. Well, the fact that neutrinos have mass, the simplest explanation for that, certainly the simplest renormalizable explanation for it, is that actually the neutrinos are just like all the other particles in the standard model. They have a right-handed partner too. The right-handed partner tends to be hard to detect because the right-handed neutrinos, because of the pattern, the mathematical pattern in the standard model, we know that the right-handed neutrinos don't couple to any of the gauge forces. So they don't feel the weak force, the strong force, or the electromagnetic force. It's natural that they're harder to detect than the rest of the particles in the standard model. And so it's natural that they were discovered later. And indeed, we still haven't directly detected the right-handed neutrinos. But as I say, indirectly, they seem to give the most plausible explanation and the simplest renormalizable explanation for why the neutrinos are observed to have mass and oscillate. If you go back to that earlier version of the Standard Model with no right-handed neutrinos, there's just no dark matter candidate left in that theory anymore. But if you now turn to the Standard Model with right-handed neutrinos, there's exactly one dark matter candidate in the theory. Okay, so when I say dark matter candidate, the two basic requirements you have to be a dark matter candidate is that, well, you have to be stable. You have to live for at least the age of the universe because the dark matter does that. So you can't just be decaying in the early universe. You have to hang around for a long time. And secondly, you can't have been detected yet except through your gravitational interaction. So you can't be one of the particles on this chart where we already detect you by some other non-gravitational means. And there's only one particle left on the chart which has those two properties. Namely, one of the three right-handed neutrinos could still be the dark matter. It's the last remaining possible candidate in this list. Now, the reason that it is not, you might say, well, why isn't that just the obvious candidate? Why isn't that the one everybody always talks about? And why do they even bother considering particles beyond the Standard Model? I think the main reason is that it turns out that the same property of the neutrino that makes it stable, turns out that in order to be stable, it's saying that certain parameters in the Standard Model are zero. There's a certain symmetry that sets those parameters to zero. Nothing new beyond the Standard Model, but it's essentially equivalent to the statement that the dark matter neutrino is stable. That's equivalent to the statement that certain parameters in the Standard Model are zero. But those same parameters, when you set them to zero, it's saying that that particle, that dark matter neutrino, is completely decoupled from the rest of the Standard Model. It only talks to gravity. It doesn't talk at all to the rest of the particles in the Standard Model. So that's good from the standpoint of being dark matter. It means it's very dark. It only talks to gravity. So it's good news on the one hand that just the requirement that it be stable automatically enforces that it's ultra dark. But you might say the bad news would be, well, you still have to somehow produce enough of it in the early universe to explain why we see the universe full of it today. The universe today has a certain measured density of dark matter that it's full of, and you have to somehow have made that in the early universe. And if this particle isn't talking to anything but gravity, you might wonder, well, how did it get produced in the first place? This mirror idea, the idea that the Big Bang is a mirror, provides a very neat explanation for that, which is that in a curved space-time, the vacuum state of a particle becomes ambiguous. Ordinarily, in the room here or, in your office, you don't really need to think about the curvature of space-time. You can treat physics as if you're working in flat space. And in flat space, in Minkowski space-time, there's a unique vacuum state that respects all the symmetries of Minkowski space-time. We don't normally think of the vacuum, the zero particle state, as being ambiguous. But in curved space, it's a fact that's in your face that if you're in a curved space like the expanding universe, different observers at different points in the space-time will disagree about what the zero particle state is. And if the universe is in one state, which one observer calls the zero particle state, a different observer at a different point in time, say, or a different state of motion, could disagree and say, no, that state actually is full of particles. According to my particle detector, there's particles present. So that happens in cosmology, and in a general cosmological space-time, in a general expanding universe, there isn't really a preferred choice for the vacuum state. You don't really know which one to choose. But the interesting thing is that when you consider this extended picture where the universe is reflection symmetric about the Big Bang, that extra symmetry does provide enough symmetry to select a preferred vacuum state. So there's a vacuum state for these neutrinos that respects the reflection symmetry around the bang. But that is different than the vacuum state that a late time observer like you or I would define. Our notion of zero particles differs from the one defined by that reflection symmetric vacuum state. So according to us, if the universe is really in the reflection symmetric state, and in particular, if this dark matter neutrino is really in the reflection symmetric state, then we will observe a flux, a non-zero flux of these particles emerging from the Big Bang into the late universe where we live. And how much emerges, how much dark matter you get, depends on what the mass of that dark matter particle is. And so, in particular, from this standpoint, there's a very natural explanation for why these dark matter neutrinos are produced in the early universe. And moreover, According to this perspective, when a cosmologist like yourself measures the density of dark matter in the universe today, they are essentially measuring one of the last remaining unmeasured parameters in the standard model, the mass of this neutrino. They're measuring it to be a particular number, 4.8 times 10 to the 8 GeV, a very specific number. This is very closely analogous to Hawking's picture of how a radiation is emitted by a black hole. Hawking famously discovered that black holes emit Hawking radiation. There, the idea is that the black hole is in one state, but a different observer defines a different vacuum state. So it looks to them like particles are being radiated by the hole. Similarly, we're saying the universe is in one state, the CPT symmetric state, but we, a late-time observer far from the bang, are in a different state, and so it looks to us like these dark matter neutrinos are emerging from the bang. As I mentioned, this leads to several predictions. One is that the dark matter is 4.8 times 10 to the 8 GeV. Another is that the dark matter is cold. That's a testable prediction. So far, it's consistent with the data, but cosmologists who observe galaxies are constantly testing to see whether the predictions of the cold dark matter model are correct. A third prediction is that if this dark matter neutrino is stable, the lightest neutrino has to be exactly massless. And actually, this observation was just confirmed by the DESI experiment earlier last week. This is a telescope that just released its second-year data and is now in conflict with anything except the lightest possible value for the light neutrinos.
It's ruled out the inverted hierarchy, I think, is the technical.
All that oscillation experiments measure, particle physics experiments measure, is the differences between the neutrino masses. So they measure these two differences, but there's two possibilities. One is called the normal hierarchy, where the masses kind of look like this, two light ones and a heavy one. And then there's the inverted hierarchy, where there's two heavy ones and a light one. But in either case, there's an overall unmeasured parameter, which is how far the lightest neutrino is from zero. So we're predicting that the lightest neutrino is down at zero. So first of all, like you say, they have not only forced the lightest neutrino down to zero, they've also ruled out the inverted hierarchy, where the two of them are heavy and the other one is light. But also for the normal hierarchy, they've essentially ruled out any non-zero value, or they've put a very tight constraint. The constraints have really pushed the bottom neutrino essentially down to zero because, in fact, much more than I had expected, because, in fact, so much so that there's this funny result that if you let the neutrino mass go negative, they actually prefer a negative value for the lightest neutrino mass. So actually any positive value is really quite disfavored at the moment. And then there's other future experiments that could test this, but those are neutrinoless double beta decay experiments that are further away. I'll give one more example of a thing that is explained by this picture, which is that, so I mentioned three properties of the early universe: that it's homogeneous, isotropic, and spatially flat. Properties that are traditionally supposed to be explained by inflation, but we give an alternative explanation. What's the basic idea? Well, what we did was we calculated this gravitational entropy of the universe. And in short, we found that it favors universes that are homogeneous, isotropic, and spatially flat. So in other words, we're saying that the reason that the universe was homogeneous, isotropic, and spatially flat is basically the same reason that the air in the room you're in is spread homogeneously and isotropically through the room. That is the state of highest entropy. So very briefly, we solved, for the first time, we found the exact solution of the Friedmann equation, where for a general universe with radiation, matter, vacuum energy, and curvature, so that's basically all the components that we know are there. And then normally people also include inflation, which makes it impossible to find the general solution. But if you don't have inflation, if you don't include it, it turns out you can solve this equation exactly. It's given by an elliptic function. That's this kind of beautiful function, but it lives on the surface of what mathematicians would call an elliptic curve, or what, to put it in terms Homer Simpson would prefer, on the surface of a donut. And all the solutions have this property that the direction around the donut here is actually the imaginary time direction. So this is the real time direction as you go around the hole in the donut. Or if you go through the hole in the donut, that's going around a circle in the imaginary time direction. This property that the solutions turn out to be periodic in the imaginary time direction, that's exactly the same thing that Gibbons and Hawking discovered in the 70s about black hole solutions, and that famously allowed them to calculate the entropy of black hole solutions. Well, you can just do exactly the same trick here now. You can use exactly their same argument to calculate the entropy of these cosmological solutions. So we do that, and then you can just ask, okay, which cosmological solutions have the highest entropy? And it turns out that they're the ones that are almost perfectly spatially flat, like the universe we observe. And now if you include perturbations, density perturbations, gravitational wave perturbations, if you allow deviations from a perfectly homogeneous isotropic universe, well, in general, they could take the entropy up or down. But if you only allow perturbations that satisfy this reflecting boundary condition at the Big Bang, perturbations that are symmetric under reflection about the Big Bang, then those turn out to all cost entropy. So in other words, it's saying that the highest entropy universes, the ones that are the most probable from a statistical standpoint, are exactly like the homogeneous isotropic spatially flat universes we observe. So taken all together, it seems to us to give a very elegant way to understand a lot of the things we see about our universe, starting from this one very simple principle, reflection symmetry about the Big Bang. And so they're derived in a sort of very principled way, but without having to add new particles beyond the standard model, without having to make up new laws of physics to explain these things or invoke new epochs that we don't actually observe. We've gotten more and more excited about it for that reason.
It's a hallmark of what your brand of theoretical physics and Niels as well is known for, which is creativity, originality, but also grounding in hard truth, hard data and facts and what we know now. And the pace of the data coming in will no doubt accelerate with, further results. We just saw great results from DESI, as you mentioned, and from ACT, and soon we'll have Simon's Observatory data as well. Nathan, now I need to take a turn because this is the part I flagged at the very beginning of the show, and in part, what my audience is clamoring to learn more about. And that's that you, Latham Boyle, high energy particle physicist, recently published, on a cosmic scale, a paper on the Fermi Paradox, which, I was thinking it's kind of like, Roger Penrose dropping a rap battle mixtape or something like that. And so I'd like to know more about what drove you to this and what, in principle, I think we should start off with kind of the cornerstone of the paper, which involves quantum entanglement. So first of all, if you could explain that. And second of all, there are a lot of, contentions by people that have been on the show many times that quantum entanglement is beautiful, it's interesting, but, fundamentally, it can't be used to transmit information. So tell us, what is the Fermi Paradox solution that you're proposing, and why should the audience members be interested in a resolution to the Fermi Paradox in this way?
A topic that's often discussed is whether when you have two particles that are entangled in quantum mechanics, whether measuring one particle can instantaneously send information to the other, whether entanglement can be used to instantaneously communicate information. And just to be clear, the answer is no. So I'm not saying anything unusual about that. But it's also known that entanglement can be used to send quantum messages. In particular, the most famous process is something called quantum teleportation that's been tested in the lab. So I got interested in this question of whether one could send quantum signals over interstellar distances. People have, like you say, worked for a long time on the possibility. It was realized back in 1959 that one could already, with human technology, send classical messages over interstellar distances using radio waves. And then shortly after, people realized you could do it with lasers. And so that ignited the search for classical SETI, the classical search for extraterrestrial intelligence. But subsequently, people discovered that classical communications and classical communication theory was just a special case of a more general type of communication one can do, which in many respects lets you do things that you just cannot do with classical communication, called quantum communication. I got interested in this question of whether quantum communication over interstellar distances was possible. And actually, there was a great pioneering paper a few years ago by Arjun Barrera here at the University of Edinburgh. He showed that quantum coherence could be maintained over interstellar distances, so that if you send signals at the right frequency, you can send qubits and have them retain their quantum coherence without decohering their information, losing their information to the environment as they travel from Alpha Centauri to us. But what I did in this new paper was I asked what it would take for maintaining quantum coherence isn't enough to send a quantum signal. The real question is whether an interstellar quantum channel can have non-zero quantum capacity. The quantum capacity is a number that measures how well a communication channel can carry a quantum signal. And if it's zero, it means you can't exchange quantum messages over that channel. So maintaining quantum coherence is a necessary condition for the quantum capacity to be non-zero, but it's not a sufficient condition. That's what I did. I calculated for the first time what is the quantum capacity of an interstellar channel.
In the world of scientific research, finding reliable information can feel like searching for a needle in a haystack. But what if there was a tool that could revolutionize the way we access and understand scientific knowledge? Powered by AI and grounded in science, Consensus brings you evidence-based insights from over 200 million research papers. It's like Google Scholar and ChatGPT had a brilliant baby, but without the clunky interface and the hallucinations. It's completely transformed how my students and I approach our work. Although I personally love Latham Boyle's quantum solution to why we haven't detected aliens, we need to be proper scientists. So let's check the consensus meter. I asked Consensus, does the Fermi Paradox have a scientific resolution? The consensus meter is now analyzing data from over 200 million peer-reviewed papers. Well, it turns out the Latham's ideas may not have caught on just yet. The results show 60% of relevant papers indicate no accepted resolution to the Fermi Paradox exists. Many researchers suggest we've overestimated the probability of intelligent life due to uncertainties in models like the Drake equation. This evidence-first approach is why the Into the Impossible podcast partners with our friends at Consensus. They deliver the sophisticated analysis my audience demands. For a limited time, use promo code Keating25 for a free year of Consensus Premium when you sign up by August 30th, 2025. Now back to the episode.
The results just struck me as interesting. So on the one hand, basically in short, one striking thing is that the laws of nature and the properties of the universe, namely the cosmic microwave background, and the properties of the Milky Way galaxy, our interstellar medium in the Milky Way galaxy, they all conspire to make it possible to build an interstellar quantum channel with non-zero quantum capacity. So that's the first important thing. But there are certain requirements in order for it to be satisfied. You have to operate at certain frequencies, but also it turns out to require enormous telescopes, and so bigger than we have built so far. So humanity has just not crossed the threshold to be in the game of quantum communication yet. That's the bad news, is that we really can't be one end of a quantum signaling channel with quantum capacity Q greater than zero at the moment. But it seemed to point to an interesting possibility, which is that, it turns out that the same condition so there's a lower bound on the size of your telescope in order for you to be one end of an interstellar channel with Q greater than zero. But it turns out that lower bound is exactly the same. First of all, the same lower bound applies to the sender. So it applies to the alien in Alpha Centauri that wants to send us a quantum message. But it also means that if they do have a telescope large enough to send a quantum signal to us, then it's also large enough to see that we don't have such a telescope, and so they wouldn't send it. An important part of the story here is that quantum communication with Q greater than zero is very different than classical communication. In classical communication, you can send out your classical signal, your classical radio wave signal, for example. You can send it out in all directions, and almost all of the photons will get lost into space. No one will detect them. On some distant star, they might just detect a tiny fraction of the photons you sent out and still be perfectly able to read your quantum message. It's perfectly possible to send. The classical capacity will be non-zero in that case, that they can receive your classical message even if they only receive a tiny smidgen of your photons. But quantum communication is very different. We would have to receive more than half of the transmitted qubits, quantum bits in the message in order to have a channel with Q greater than zero. That's because if you could do it with any less than a half, that would violate the so-called no cloning theorem of quantum mechanics, or the no Xerox principle. You can't Xerox a quantum state, and that prohibits a channel with Q greater than zero if you receive fewer than half of the photons. But so it means that if it is the case that if there are intelligent civilizations in our galaxy, if they're communicating quantumly with one another, it means by necessity, they have to do that in a very directed way. They have to be basically sending their signals so that they travel essentially from the sender's telescope to the receiver's telescope. Essentially, they're not spilling photons all over the place. They have to be sending them in a very directed way just to get a non-zero quantum capacity. If they can see that we do not have a telescope capable of receiving that message, they wouldn't send it to us, and we would be none the wiser because they would be sending signals around that we couldn't see. Now, do I believe that this is the real explanation for why we don't see evidence of large-scale intelligent life elsewhere in the galaxy? I really have no idea. I guess if I was going to bet, I maybe might bet against this. It sounds a little bit like science fiction to me, but it just struck me as very interesting that the laws of physics essentially, imply that, first of all, there is this more advanced type of communication, much more powerful type of communication one can do, that already, 100 years into our technological civilization, we're already kind of trying to progress. We're already have discovered it and are beginning to progress ourselves to try to learn to use it, to try to learn to use quantum communication in various ways ourselves and on Earth. So on the one hand, there's this more powerful communication option available. And on the other hand, because of the laws of physics, because of the laws of quantum mechanics, basically, if you did imagine that there were advanced civilizations communicating quantumly, that seems sufficient to explain why we don't see any sign of that. I don't know. It just seemed like an interesting enough conclusion that it seemed worth pointing out. I just noticed no one had calculated the capacity of one of these interstellar channels. And so, I guess nobody had really noticed this.
The question I get mostly is, these objects that people claim to see defy the laws of physics. And I mean, you're one of the top physicists alive today. What do you make of these sightings and claims and so forth of technology, of biological material? Do you believe that? I mean, that would be the ultimate evidence that the Fermi Paradox is not a paradox, right? They're here. So what do you make of these sightings and even claims of physical, artifacts from either craft or biological specimens?
So there are a lot of these claims where the evidence is not available for scientific scrutiny, or people are asking you to take their word for it. For those claims, I personally don't believe them until there's evidence that's kind of available for scientific scrutiny. There's the other type of claim, which is the sort of claim that has been made by Avi Loeb. One thing that definitely has been detected are like Oumuamua, are objects from outside the solar system that have been detected. And then there's a question of whether those may be of technological origin. That seems like a very interesting question, which in principle can be investigated scientifically, maybe not with Oumuamua because it's too far away now, but with other objects like that. So that's in a totally different category. I mean, there's not strong evidence that anything like that is of extraterrestrial origin. If further investigation of that sort of thing showed that it was, well, that would be very exciting and great. I mean, I personally, based on no information, I kind of wouldn't bet much money on that turning out to be the case, but who knows? And I think, speaking of, I think that Avi also has meteorites that he's recovered from the ocean floor that also, I think he thinks are of extrasolar, came from outside the solar system. That sort of thing, I think that sort of investigation is very interesting. And I really don't know whether it'll turn up what it'll turn up, but that's in a completely different category.
And then speaking of meteorites, I always like to mention that for my guests like Latham, but in the academic community, I give out these meteorites to anybody with a .edu email address, but unlike Latham, they have to live in the United States. So to get those, you go to briankeating.com/edu if you do live in the U.S. But if you don't have an edu email address, or you don't live in the U.S. and you do have one, go to briankeating.com/list and you'll sign up, and we'll have a lot of kind of debriefing from this episode, which has been so much fun for me, and I know for the audience as well, Latham. But as we wrap up, we started off talking about fundamental symmetries and how a particle physicist got into all these disparate kind of interesting intellectual terrains and landscapes. But I guess, when I think about how we've journeyed today from, discussion of CPT, symmetry, to then, a mirror universe, wrapping up with a return to this question that I posed at the top about how a particle physicist could get interested in solutions to one of the most vexing conundra of all time, the Fermi Paradox. So let me ask you this final question. If both of your major threads that we talked about today, at least CPT, symmetry, in the mirror universe, and interstellar communication, quantum signaling as a solution to the Fermi Paradox, or an approach to it, if both of those turned out to be right, what kind of universe would we really be living in? And what would it say about humanity's place within it?
I find it very, fascinating. I think, like everyone must, that, like we discussed before, things somehow the universe began in this very symmetrical soup with just tiny perturbations, and then they grew over time into galaxies and planets, and at some point came awake and came alive, and then ultimately became conscious and began developing explanations and understanding of the universe. It just seems like a very fascinating but puzzling question how that happened in the first place. That maybe the modern take on the Fermi paradox from a cosmologist standpoint would be that the evolution of, our scientific understanding, at one point we started off thinking that we were at the center of the universe, but then kind of generally speaking, the Copernican principle has held true. That, we discovered that no, we were actually not at the center of the solar system. We were just one of a bunch of planets orbiting around the sun. And then the solar system was not the only solar system. It was one of maybe 100 billion solar systems in the Milky Way, maybe. And then the Milky Way itself wasn't the only galaxy. It was just one of many similar galaxies spread throughout, 100 billion of those in the observable universe, and who knows how many more beyond. And so that whole trend has been to say that we're not really in a special place in the universe, that we're in a kind of typical place, or a place that's reproduced many times over. And, so it would be a big reversal of that trend if it turned out that we were somehow the only planet with life in the galaxy or in the observable universe or something like that. I haven't the faintest idea whether it is or not. Everyone seems to have a strong opinion about whether that's true or not. I just feel completely perplexed about whether it's true or not.
Latham, it's been a wonderful conversation. We'll have to do it again. I'll be in Edinburgh this summer. Maybe we'll do one in person.
Okay, that sounds great.
And I'll bring you a meteorite. I'll bring you a meteorite.
I was going to ask, the way you phrased it, I think what you meant was that you can't request a meteorite if you're outside the United States. But
you can request it, I just can't ship it. Yeah, we will definitely get a meteorite. I will bring you a meteorite and maybe even some more swag. Latham Boyle, thank you so much for joining us late in the evening, or later in the evening for you than it is for me. There's so much more left to cover. I can't wait to our part 2.
Thanks. Likewise.